Hi, so welcome to Math 408, L functions and sphere packing. Today we're going to talk about the Gauss circle problem. Okay, so I think I showed something like this, quite a while ago when we were talking about interpolating functions. And we were talking about, well, how many points do we need to interpolate? Depending on the form of the function, a different number of points will suffice. If you have, too many points, of course, it could be wasteful to be spending time getting them. The other question is, it might be easier to get values of derivative or other things all at one point rather than getting more points. And so I mentioned a formula involving a function, its Fourier transform and its derivative, and this was supposed to be a function that was radial. So what does it mean for a function to be radial? So what is a radial function? And give me an example of an important function from the world that is radial.
A radial function is a function where its value only depends on distance from the origin.
Excellent. So do you know any examples of radial functions in the real world?
Gaussian.
Force of gravity, forces.
Force of gravity, classical gravity, classical electricity. These are radial forces. They decay like 1 over r squared. So we're going to be looking at a lot of radial stuff today. So the first is the famous Gauss circle problem. And what I love about this is you can get extremely excited and think that you have made a major advance just because of a confusion of notation. So the question is, consider the standard integer lattice. How many points lie inside a circle of radius r? There are two different ways of phrasing this. One is a circle of radius r, one is a circle of radius square root of x. Does it really matter which one we do?
No.
No, but it will change the power of the error term. So be very careful when you're looking at things that you see. Are we talking about a circle of radius r or a circle of radius square root of x? Why might we do things of radius square root of x?
Because then the area of the circle scales linearly, so like the number of points is linear also.
Beautiful. Then the area is scaling linearly. So here is the first question. What do you think the main term is? In other words, how many lattice points in the standard lattice do you think are inside the circle of radius r centered at the origin?
Should be order r squared.
Should be order r squared. Okay, so can you do better than order r squared?
Well, we'd expect about 1 point per square unit, probably.
Okay. But so I agree that it's order r squared, but is it 1,000 r squared? Is it 1/3 r squared?
I would think it's about pi r squared.
About pi r squared. Okay.
Can't you get a bound of like r and then like root 2r or something, or 2 root 2r on the outside? Because you could inscribe a square inside the circle, put a big square on the outside of the circle, and that should give you lower and upper bounds on it.
Okay, so now you have to be a little bit careful where the points lie, but you're on the right track. And what's the area going to be between those two squares?
The difference between them two, or the?
Well, let me see. So I'm going to switch to. So I think you were saying the following. Let's take our circle, and then oops, we'll do the circle. And then what we'll do is we'll take some squares. We'll take a square.
Yeah.
Outside, and then I can take a square inside and try to get some bounds with this.
Mm-hmm.
do you think that the error is going to be of order, what size do you think the error is going to be?
Shouldn't it be also r squared?
Right, so the error could actually be quite significant when you look at this. You know, I'm having fun playing with the different paints. Oops. And so, do we expect that this area in the orange or the area in the yellow is going to be growing like r squared?
Yeah, it should grow around 2r squared, right?
So if I just draw a little bit like this and just try to look at what's happening, you know, I've got a triangle over here, and I'm going to have a significant amount in this little slice over here. And similarly over here, I'm going to have a significant slice over here. So if I just do two giant squares like this, the error is going to be of size r squared. It might still be enough to give us a semi-decent main term, but it's not going to be as good as possible.
You could probably do some fractal thing where you like remove the four corners of the big square and then add in the four, just like, I don't know.
Well, so the more work we try to do, we could try to have not a square, but a, say, octagon, or keep going up in powers of 2. But then, of course, we have to worry about where the lattice points lie.
Yeah, that's what the square is really nice because it'll contain all points between.
The square is very nice. I absolutely agree. So shifting back to what do we expect the main term is going to be? What multiple of r squared? Any thoughts?
2r squared.
Okay, why 2r squared?
Because of the main term in the error or
The main term in just how many lattice points?
Oh, pi r squared.
Pi r squared. Yeah, because the circle has area pi r squared. Each lattice point is in a square with itself as center, you know, of side 1. And so we would expect that it would be of size, you know, comparable to the area. What could you do to see if this is a reasonable answer, a reasonable conjecture?
We could like try to scale it up and just count how many points there are approximately and see how it grows.
And so how would you count the number of points? What would you do?
Write a program, maybe.
Write a computer program. So, you know, if you write a computer program, here's a printout from Math World. Here's fluctuating.
This is pretty convincing.
I'm sorry?
This is pretty convincing that
it is pretty convincing.
Lands around pi r squared.
Yeah, although I'm not quite sure why they have the line at 3.142.
It's just under.
It is just under that. And it is above the 3.140, which is right here. You know, 3.1415 would be about 3/4 of the way up. And so it's looking pretty good. And so here, your NR is the number of points, is the number of points, lattice points in a circle of radius r, and E of r is the error, pi r squared is the predicted main term. Okay. So we believe we know the main term. We believe the main term is pi r squared, and we'll see very shortly a quick answer, a quick argument that yes, it is pi r squared. What do you think the issues might be when we try to count? What might be the difficulty?
The edge point, or like the arc.
Yeah, in what way?
Well, you know, if you're at a circle of radius 4, you're going to contain the point, you know, 0, 4, 4, 0, negative 4, 0, 4, right? But, you know, what about 3, 3? Right in the diagonal off, it's somewhat unclear for which values of like whole integers you'll contain those edges.
Right. And the problem is going to come down to, are we talking about the number of points inside the circle or inside or on the circle? Does that make a difference? And so here is, a plot of, a couple of different radii and the number of points that you have on the boundary. And so there's also a little table here that gives you the smallest radius, such that the number of points on the boundary is at least the following. Do you notice anything about these numbers?
Powers of 5.
So not quite powers of 5.
Oh, multiples.
So multiples of 5. So this is interesting, do you think it's always going to be a multiple of 5? I do love how for 76 and 92, the answer is, at most about 2 million or at most about 49 million.
Those are some good bounds.
Those are some good bounds. It's not quite as bad as Ramsey theory, but what do you notice about the values of LR that it's displaying?
They're 4 mod 8.
So are they all 4 mod 8?
Not 1.
Not 1. And so 1 is the degenerate case of a radius of 0. But everything else looks like it's 4 mod 8. So there could be some symmetry. Are you surprised that there could be things of 4 mod 8?
No, because there's 8. You can break the circle into 8 parts that should be the same. And then you also have the corners.
Right. Are we ever going to have something on the diagonal?
No.
No, because it's irrational.
Right, because if we had the point, x comma x, and we wanted that to equal the radius squared, you'd get 2x squared equals r squared. And then that would mean the square root of 2 would have to be rational. So we know there's not going to be anything on the diagonal. So if we break it up not into quadrants, but into eighths, there should be some symmetry, replacing xy with yx and then putting in negative signs as well. So there's some symmetry here. So then the question is, why is it a factor of 4 versus a factor of 8? What's going on? How many points does everything generate? So we almost have it. It looks like we basically can switch x and y, put in minus signs, but then doesn't it seem that every point generates 8 points? Why is it 4 mod 8?
Because x0, negative x0,
Good.
0 y.
We have the points plus or minus r 0 and 0 plus or minus r. So we always have these 4 points on the coordinate axes. And then every other point comes with 8 copies. So, again, this is one of the things I love looking at tables like this. They tell you a lot. And just looking at it a little bit, it starts to become clear what you might want to try to prove. I don't see any way immediately to look at this and get the multiples of 5. But part of that is because this is supposed to be the smallest r where such things happen. And we do know when r equals 5, that's when we do start having some interesting points coming into play. Okay, so we've identified the main term. Let's try to prove it now. And so here is a plot of points. And what we're doing is we're looking at 2 different circles. And the real question is, what radii do you want to take for the circles? And there's a couple of ways that we can do this. If we take something here that has a smaller radius than the black, let's say the black is the one we care about, then we know any lattice point inside the green, any square is going to be entirely contained in the black. And similarly, anything that's in the black or on the black is going to be entirely contained, I don't know, would you call that magenta?
Pink.
Pink? So I think I might have the wrong image here as to where this is from, the wrong reference. I'll double check that later. But can we use this now to prove that the main term is pi r squared?
It looks like the red and green circles are of a fixed distance from the black one, or at least a bounded distance from the black one.
So what distance would you say it would be? It's not 1.
It's root 2.
It's root 2. Why is it root 2?
Because that's the longest distance in the circle. In the square, in the unit square, the diagonal is root 2. So this guarantees that they're...
The diagonal is square root of 2. So any point in here is at most root 2 away. So we have a circle that's root 2 less and a circle that's root 2 more. And so if we want to look at the area that's the difference between them, well, it's pi r plus root 2 squared or pi r minus root 2 squared. The differences is going to be of size r when we just expand out the r plus or minus root 2 squared. So the region over here between these circles is going to be of order r. Another way of saying it is the perimeter of the circle is of order r, and we're just taking some kind of tubular region around it. Okay, so now can you give me a rigorous proof that every square that touches the green one is going to be entirely contained in the black?
Yes.
And the proof is?
If there's some point, if the square touches it, then there's some point in the square, which is on the circle. And every point in that square must be at most root 2 away from that point in the circle.
Perfect. So we know if we take, the squares, any square that is either inside or on the green never reaches into the black. And every square inside here is going to give us a lattice point. So the area of this green square is going to be pi r minus root 2 squared. And that will be less than the number of lattice points we have. And similarly, if we look at the magenta, pink, whatever we're calling that, that's going to overcount. So do we agree that the main term is going to be of size, is going to be pi r squared, and the error term is going to be of size r? Sound good? Do we agree that the main term is pi r squared and the error is at most of order r?
Yes.
Yeah.
Yes. What do you think the true size of the error is? Do you think it really is of size r, or do you think it might be smaller?
I think it's a size R.
So you think it's size r. So you think that this argument is actually pretty tight, that we really are not missing too much by these approximations.
Yes.
Going back a little bit, we were talking about issues with points on the boundary. And if you look at the smallest r that has this many points, it looks like r is growing a lot faster than the L of r. So for instance, if we take 540 times 540, we get 291,000, which is of the size 160,000. If we do 300 squared, that would be 90,000, which is again of the same order as R. So looking like the number of points that could actually be on the boundary, that looks like it might be of size square root of R, not of size R. But of course, that's a very special type of error. That's the error from the points being exactly on the boundary. We could have other errors of points being, just a little bit high, or just and not counted, for example, or just a little bit inside, and we maybe are counting them, and maybe we wouldn't. So the question is, what do we think the error? How do we think the error is going to grow? As a nice challenge problem, can you prove that given any number n, you can always find a radius such that there are at least n points on the boundary? So this shows that for n up to 540, we can do it. But what if I give you n is 2020? Can you give me a radius where you are guaranteed to have at least 2020 points on the boundary? Do you think
yes.
Points? Okay, so that's a nice fun. I'll make that an extra credit challenge problem. Is come up with a way to show that you can have arbitrarily many points on the boundary. When you do this, it would be interesting to see if your proof is constructive or not constructive. By that I mean, do you actually tell me the radius that you need? And then if you do, we can compare and see how does your number of points depend on the radius. Is it of comparable size, or like this? Is it more like the square root size? Okay, so we talked about how we would prove that, and this proof gives an error of size R. So the question becomes, if we write the number of points as pi r squared plus an error, what is the smallest theta we can take such that the error term is at most r to the theta? And if you want, you could actually change this a bit, and you could say, well, look, maybe I allow myself to put some universal constant c here. And I don't really care what the value of c is. I care how it grows with r. That's the thing that really matters. So we had a conjecture that theta equals 1. We know theta can't be, the best theta can't be larger than 1, because we've already got errors of that size. Any other thoughts about how small we might be able to take theta? Does anybody think we can go smaller than 1?
Well, from the boundary, it seems like theta should be at least like 1/2.
Okay, why 1/2?
Because that would be like the square root of r.
I'm sorry? So could you explain why you think it should be 1/2? Because the boundary has length r. I'm not saying you're wrong. I can't, because it's an open problem.
Yeah, never mind.
But you're on the right track. So here's some history of the various values of theta. And you can't look at this table without smiling if you're an analytic number theorist. You'll see, we're going from 24/37, which is 0.64865, to 35/54, 0.64815.
Then we get pretty good increase with 278 429ths.
Yes. And so it becomes an interesting question. When do you have a truly new method that really gives you something phenomenal? This is one of the greatest increases for here, in the 4th decimal place. But
wait, what happened in?
even less.
these should be chronological, right? Like, why did Chen and Kolesnik in 82 like say that it was 30, we could get a bound of 35/54 when Vinogradov in 35 had 34/53.
They're doing their best, Isaac.
Good question. So I pasted this, I think, from Math World. And so, some of these things are undated. So for instance, I don't know when the Kolesnik is. It may not have been known. The other thing is, sometimes what happens is you can get worse bounds with less effort and less ingredients.
Like assuming less things.
Assuming less things. And so when I was at Princeton, I was the second reader on an undergraduate thesis. Andrew Wiles of Fermat's last name fame was the first reader. He was the thesis advisor. And the thesis was about extending a beautiful result due to Maser, that if you look at elliptic curves, there are only finitely many possibilities for the torsion subgroup when you look at rational points. And there's a generalization of this to number fields. And the student was trying to understand the generalization, and at one point it uses some extremely powerful machinery from algebraic geometry. It uses the Weil-bound. And so I was talking with her, and I asked her, do you understand the proof of the Weil-bound? And she says, no. And I said, neither do I. But I was fortunate I had two advisors, Peter Sonic and Henrik Ivanit, who is listed over here. And Ivanit was extremely focused on teaching us how to do counting on our fingers and do these quick estimates. And if you don't want to get the full strength of the Weil-bound, if you just want to get some power savings, there's a really nice fourth moment calculation that you can do that gives you a bound that's good enough for many practical purposes. It's not the best, but it's good enough for what we needed here. And so a lot of times there is value in getting a sense of just how deep is the result, especially because if your result is conditional on something else and then a mistake is found in that, then all of a sudden your result is no longer good. So sometimes when you write papers like this, you say, we need a bound of a sum or an integral or an expression that has a power savings of theta. And you leave theta as a parameter for all your calculations. And then in the very last line, you now say, and the best known value of theta is by blah and blee, who proved you can take theta equals whatever. And then this way, if there is a mistake, you just go back to the previous. What's the other advantage of writing it like this? So one is if there's a mistake, you can immediately go back to a previous result and weaken your result. But what's the other direction?
If someone gets a better bound, then your result.
If someone gets a better bound, you can now immediately plug that into your result and see how it improves. So in the list like this, a lot of times the first result is not too concerned with doing anything optimal. And then later, people chase down the constants and they try to optimize the method. And then eventually you start to reach the limit as to what the method can provide, and then you have to shift to an entirely new perspective. So one of the first examples of something like this was in the Riemann zeta function, trying to count what fraction of the zeros are on the critical line. And the first breakthrough was by Selberg, who showed there exists a positive percent. He didn't bother calculating what that positive percent was. You could chase down his arguments, you could make it explicit, but it was just the fact that there is a positive percent. When you look at these numbers, what do you think the limit might be?
.5.
0.5. Why 0.5?
Because it's going down. I don't know. It seems like a natural end. And we talked about how it was 0.5 earlier. I don't know.
So you are correct. 0.5 is a much more natural number than 0.6. Yeah, but it's not clear that it is going all the way down to 1/2. as opposed to, is there some irrational number that it's converging to?
Yeah, maybe it's going to like pi fifths or pi sixths.
It could be.
I think phi minus 1.
Phi minus 1. That would be fascinating if the golden mean surfaced here. As an aside, if you've done Monte Carlo calculations where you try to find areas of curves by choosing points at random, the Fibonacci numbers in the golden mean actually work beautifully for a refinement of Monte Carlo where you don't need to know ahead of time how many points you're looking at. So the Fibonacci numbers in the golden mean do arise in some of these geometry lattice problems. We just quickly share that just because it's so beautiful. Okay. Can people see my screen? Can people see the Microsoft Paint screen?
Yep.
Yeah.
All right, so let's imagine we have a unit square. And now let's take some kind of strange shape. Oops. I'll do it like this. And we want to figure out what is the area of this shape. So there's a lot of ways to do this. One way to try to find the area of the shape is to just throw dots randomly. And what you'll do is, here's a dot. And then I throw down another dot, and then I throw down another dot. And so on and so on. And if I throw down and dots, what fraction are inside? That should be a really good approximation to the area. And the larger n is, the better approximation this is. And this is often called Monte Carlo. Now the problem with this, of course, is maybe you're a little bit unlucky when you're throwing down the dots. So what might you use to try to minimize danger?
To like use a finer and finer grid of dots.
So you might use a lattice. You might choose, say, the integer lattice, and in that way, everything is going to be a uniform spacing that you're putting it on. The problem is, what if you choose to do a m by m grid? So n equals m squared. Okay. And imagine it ran in less time than you expected. So you actually have time to add a few more dots. The problem is you've already created your grid. You can't go now to the n equals m plus 1. We can't just go to that because we may not have that many more points to add. There is a nice way to do this involving the Fibonacci numbers and the golden mean, where you are putting points on using the golden mean so that it's not a lattice, but it keeps filling in the space so that if you have more time, you can just add more points without any trouble. So the comment about maybe the golden mean surfaces is actually not a bad comment. So what I want to do now is talk a little bit about the philosophy of square root cancellation. How many of you have never heard of this philosophy? So everybody has heard of it to some extent?
No, none of us have.
Oh, none of you have, okay.
I thought you said never heard of it.
Sorry. I have gone to see the doctor and the dentist And unfortunately, I have an issue where I cannot close my jaw and I am having a little trouble talking, so my apologies. You have that plus the Boston accent today. So for many problems, imagine you have n random terms and each term is of size 1. So if each term is of size 1 and they're completely random in phase, say plus minus 1, or more generally e to the I theta, you might expect the sum to be 0. And the central limit theorem often kicks in and says that the fluctuation should be of size square root of n. So for homework, I want you to write a computer program to do at least 100 million tosses of a fair coin, do plus 1 for each head, minus 1 for each tail, plot where you are after each of the first 10,000 tosses, also plot where you are every 10,000th toss. And then compare your plots to plus or minus 2 root n. And so the square root of n is the standard deviation. Twice means 2 standard deviations. So for the most part, you should be within 2 standard deviations. If you have any issues coding, just look below or happy to chat. It took less than 5 minutes for my Mathematica program to run and to do this. Let me just quickly show the output. Okay. So now let me toggle again. So you might have seen these in random walks. They used to do this to model Wall Street. And so I am plotting where I am every toss for the first 10,000 tosses. And you can see I do break outside that band, but not that often. And then over here, I'm plotting, I think 100 million tosses, but I don't want to save 100 million points into my data file. That would just be far too much information, and we really can't see things on that scale. And so I'm just plotting where I am every 10,000th, so zooming out a little bit. And you can see in this case, we actually stayed within the band the entire time. So I want you to be able to just write a short computer program to do something like this. If you have any trouble doing this, happy to help you. This is just a really good skill to have when you leave college, the ability to quickly simulate and get some sense of what is going on. Okay, so toggling back. So the central limit theorem is one of the greatest results in all of mathematics. It is absolutely beautiful. It kicks in so many different times. We need to figure out what is the cleanest notation to do this. So the next couple of pages I've actually just pasted from the probability book that I wrote. So if you've taken probability with me, it's exactly the same stuff over there. We're going to do a very simple case where we flip a coin and we have probability 1/2 of a head and probability 1/2 of a tail. And instead of doing 1 for a head and minus 1 for a tail, I'm doing 1/2 for a head and 1/2 for a tail. And I'm doing not n tosses, I'm doing 2n tosses. This is just to make the algebra a little bit nicer. It really makes no difference. So the main result that we're going to need is Stirling's formula. I know we've talked about the gamma function in class, but I don't think we've talked about Stirling's formula. Is that correct? So n factorial is approximately n to the n, e to the minus n, square root of 2 pi n. We'll use really bad writing to do this. It's a fun problem to try to prove this. Any thoughts how you should get your hand on n factorial?
Take a log.
Yes! Why take a logarithm?
Because then you're just
the sum.
Yes, whenever you see a product, take a log. Whenever a log to get a sum. Now the log of n factorial is equal to the sum at k equals 1 to n of the log of k. And what would that be approximately?
Do the integral instead of the sum?
Yeah, integral x equals 0 to n.
So what, n log n?
Log x dx. Yep. The anti-derivative of log of x is x log x minus x. It is okay not to know what an antiderivative is. It is not okay to have the wrong antiderivative, because you can always check by taking the derivative. And so if you check, you can see that this is the correct antiderivative. You can worry a little bit about what error terms are. Should we go to n? Should we go to n plus 1? It's really the integral test. And so it's a nice exercise, go through an argument like this and get a rough order of magnitude of what n factorial is. And then in terms of how you would guess this, if you just started with x log x and you take the derivative, well, when you take the derivative of x, you get 1, so you get log x, which is great. But then when you take the derivative of log x, you get a 1 over x. So the derivative of x log x is just log x plus 1. And that's why we have to subtract x over here. Okay, so shifting back. So we're going to have a bunch of Bernoulli, this should not really be binomial, these should be Bernoulli random variables. Each of these is 1/2 with probability 1/2 and minus 1/2 with probability 1/2. Oh, no, never mind. I'm sorry. I misread what I did. This is the probability. I'm sorry. They're all plus or minus 1. My apologies. They're all plus or minus 1. And so we're 1 with probability 1/2, we're minus 1 with probability 1/2 as well. Okay. So we have our independent binomial random variables. We can calculate the mean. It's just 1 times its probability of 1/2 plus -1 times its probability of 1/2, which is 0. We can similarly calculate the variance, and the variance is just 1. So we let S2n be the sum of the first 2n tosses. So the mean is 0, and this is because the expected value of a sum is the sum of the expected values. If you haven't done probability, do not worry right now. I'm just trying to motivate the philosophy of square root cancellation. And then it turns out if your variables are independent, the variance of a sum is the sum of the variances. So we expect S2n to be of size 0, but with fluctuations of size square root of 2n. And so now we want to consider what's the distribution of S2n. So we know it can never take on an odd value because we have an even number of tosses. And so it has to be some number of heads, some number of tails, and the difference is going to be an even number. So let's say that we have 2n minus k tails, and I'm sorry, k heads and 2n minus k tails. Then S2n is going to be, there's a typo here. This should be n plus k heads and n minus k tails. Sorry about that. So we have n plus k heads, n minus k tails. No. Sorry, well, all right. This is correct, but that's not what I use on the next line. So this would be, we would have, if we have exactly k heads, we have 2n minus k tails. So then S2n would be 2n minus 2k. I don't want to look at 2n minus 2k. So instead I'll say, what if I have 2k as my excess of heads over tails? Well, if I want 2k as my excess, I would have to have n plus k heads and n minus k tails. How many ways can I have n plus k heads and n minus k tails? I have 2n tosses. I have to choose n plus k of them to be heads. So I have 2n choose n plus k, 1/2 to the n plus k, 1/2 to the n minus k. Oh, that's not so bad. That's just going to be 1/2 to the 2n. The difficulty now is, what does 2n choose n plus k look like? And that's where we just now start to use Stirling's formula. So we take Stirling's formula and we write this as 2n factorial, n plus k factorial, n minus k factorial. We expand everything out and we start doing some of the cancellations. We see beautifully a 2 to the 2n that's going to cancel with the 1/2 to the 2n, great. And then we have this expression over here that we have to finish. And so it's just a bunch of algebra. And so you might make some kind of naive argument that, well, maybe this looks like 1 plus k over n to the n. Maybe this looks like e to the kn. This looks like e to the minus kn, so maybe they cancel. And then maybe have to worry about the k and the minus k. So maybe it's e to the k squared and e to the negative k squared. So maybe e to the 2k squared over n. As you know, some kind of way of trying to get a sense of what's going on. It turns out that that argument is a little bit naive. You need to be a bit more careful because it doesn't converge to that. It actually only converges to something with an exponent half of that. The best way to attack this is to use logarithms. So as always, this is the general theme of any class of mine. When you see a product, take logarithms. And so if we take logarithms and do the calculation out, you'll get the n plus 1/2 plus k coming down, the log of this, Taylor expand this, and you'll see basically everything cancels. So we can't just say that this is just e to the w. So you again, as a good exercise, go through, do the calculation in a little bit more detail. The next thing we need to do is we need to figure out roughly how large can k be. I'm not going to go through the calculation. It's here. It basically tells you if you take k a little bit more than square root of n, say n to the 1/2 plus epsilon, using weak results like Chebyshev is enough to show that its probability is negligibly small. And again, if you haven't seen probability, don't worry about it. And then you can just show with a little bit more work that this product is going to converge to e to the k squared over n with an error of size tending to 0 rapidly with n. And so again, this is just taking the logarithms, as I said, going through and doing all the calculations. And so now, when the dust settles and we put all the pieces together, we get something that's e to the negative k squared over n. So it's close to a Gaussian. It's not quite there, but you have to remember that we only have something that can be non-zero at the evens. So really, whenever you get a value, it's over a window that's twice as large. And so when you put that in, that's going to make everything work out. And the rest is just doing the algebra to rewrite it in terms of a Gaussian with the mean of 0 and the variance of 2n. And then that is the end of the calculation. If you want, as a nice challenge, you can try to do this for a probability other than 1/2. The algebra gets a lot worse. The best way to do this is really through the central limit theorem. But the main idea is this philosophy of square root cancellation. So the last thing for today is, why do you think that's related to trying to estimate the error on the circle problem? So what's the connection? So do we agree that we have a band of order r around the perimeter of our circle of radius r? And in that band, we're going to have some of these squares, and sometimes the lattice point is going to be inside, sometimes it's going to be outside. And if you want, call it a +1 if it's inside, and a -1 if it's outside. And so when we're trying to estimate things, maybe this is similar to that philosophy of square root cancellation, that we're adding on the order of our objects, where some of them are going to be +1s for inside, some of them are going to be -1s for outside, and we expect some cancellation in terms of how many there are, in terms of our correction to our areas, and that might be a reasonable explanation for why the error term should be like square root of r. So for the next class, I'm going to give a very high-level introduction to the Fourier transform in several variables, generalization of Poisson summation, and how you can actually get a better argument and get down to an exponent of 1/3. Now, an exponent of 1/3 should be very surprising because that's less than a half. The reason it's an exponent of 1/3 is because we're doing it with a radius of square root of x. And so it's not the remarkable savings you might think. It's really a 2/3 when the radius is out. Right. Any questions?